Okay, so it's now 13:51 according to my computer's clock. I think we're still missing a few people who are at lunch, um, but in order to make sure we have enough time to actually do some of these exercises, I think we had better get going. So thanks those of you who've put in your responses in that poll. I'll add my choice there, which unfortunately imbalances it a little more. As I say, this wasn't intended to start anything. I was just interested to see if anyone, if there was any overall preference, and there does seem to be one for Vi or Vim, just because we will be editing some text files during this session. And well, I think as we do have at least one person in every category, I'll sort of just show all of them being used, I suppose. Before we get going properly, can I just check you can hear me okay? There isn't any noise?
Yes. Yes.
Okay. Perfect. Thanks. Thanks, everyone. Okay. Perfect. Okay, then. Oh, we've got some more responses in now. More people saying yes to Vi and Vim. But yeah, we'll see all of them in use in this session. Okay, let's get going. I'll finish that poll. Please don't let that, color your perceptions of anyone. Let me just get my screen sharing again, and then we will move on with understanding the scheduler. Okay, so okay, so you can hopefully see my terminal again, as it was where we left things. And okay, so at this point, Python is essentially set up and ready to go. We don't need to worry about that now. We can just, when we need it, start using it. But what we need to do before we can run what we'll call jobs on the system is we need to understand how access is determined onto the back end of ARCHER2. All of us have hopefully got on there now. I haven't heard from anyone who's had any issues getting logged on. So hopefully we're all on one of the login nodes right now. So here I am again. I'm on login node 02. You might be on any one of the others. But that's just the login node. And as I showed you, there are a whole bunch of people logged onto the login node. All of these are users, and you might be one of them. So we're all here on the login nodes. There are 4 of them, but as we saw, there are thousands of compute nodes. And on top of those thousands of compute nodes, which are used for the big, heavy lifting simulations, we've also got the 2 data analysis nodes. So those 2 data analysis nodes, which we're actually interested in. But how do we get access to them? They're there on the system, they exist. The login nodes are connected to them over a network. They're all connected to each other over this very high performance network that allows them to work in concert to crunch lots of numbers very, very quickly. But we haven't seen anything so far about how to actually access them. If you've used any sort of cluster before, you've probably interacted with what's called a scheduler. So that's a piece of software which runs in the background. It runs on all of the nodes throughout the cluster. And we as users interact with that piece of software, the scheduler, to get access to resources. When I say resources, what I mean here is essentially time on the compute nodes and the data analysis nodes, time on the back ends for us to do work. That's what I mean by resources. So the scheduler is a piece of software that's running there, and we make requests to it to say, I would like one node for, let's say, 8 hours, 6 hours, 24 hours. And while I have that time on that node, I want to do some work. I want to maybe run a huge simulation of something. Maybe I want to run a Python script, as we will be doing, to read in some data, do some analysis, maybe make a plot. That's what we're going to be doing. So this scheduler is there running in the background. Let's just take a quick look. If I run a command, and you can do this too, SQ, and then press enter, we'll get in a second a load of output. It's actually, let me just see, I'm going to make my text just a little smaller. If that's difficult to see at all, please say. That maybe fits a bit more in to the screen so you can see without the text wrapping across. What we've done with that command, SQ, we've essentially listed every job, as they're called, that's currently in the scheduler. So a job is a request to the scheduler from a user to do work. And what I'll do is I'll then pipe this onto less. This will make it a bit easier. So this is all of that output, but I'm just starting at the top. So you can see this output comes in columns. We've got some job IDs, partitions, names, users, status, time, nodes, quite a lot of information here. So let's go through these columns. We've got a job ID. That's basically an ID for a given job. So a given request to use resources on the back end of ARCHER2. Each request has a number identifying it. You can see they're often sequential, as each new job gets an ID that's incremented by 1. Then there's some information here. This is what's called the partition. It's basically saying which type of node is it running on. So we've got some jobs running on the high mem nodes. So remember I said that there were a few hundred compute nodes which had double the memory of the standard compute nodes. So these jobs are running there. Well, actually, these are waiting there. Then we've got a name for the job. So when you create a job, when you say I want, one node to crunch some numbers, you can give that, a name that tells you what it is. Then we'll see the user who made that, who set up that job. Then we've got a column here, status. These all say PD, that means pending. I'll talk a little about that. Then we've got some which say R, that means running. Then we've got another column for time, 0. Okay, these are all 0 because they haven't started running yet. Then we've got some which have been running, well, in this case, almost 21 hours. So this is 20 hours, 53 minutes, and 39 seconds. These have been running. This column here, nodes, tells you how many nodes are in that job. So, in this case, this person said that they wanted for this piece of work 256 nodes. This person wanted 11, wanted 1 here, 10, 9. And then the last column is either a node list or a reason. So the status here, PD, means that that job isn't running yet. Someone's made the request. They've said that they want however many nodes for however long to do whatever work. And then you send that off into this piece of software called the scheduler, and the scheduler puts it in a queue. If it's running, it will have R. If it's waiting to run, it will have PD, so pending and running. If it's running, it will, in this final column, actually tell you which nodes that job is running on. So this job is using 20 nodes. It's running at the moment for nearly 21 hours. And it's using these nodes. So you can see these, that the nodes have names. Just as we're logged into LN 01, 02, 03, or 04, the compute nodes have names MID 002756. NID 002757. And these list the ranges. So all of the compute nodes have names beginning with NID and then some number. And you can see all of these numbers here. Down here, and this is more of interest for us, are some jobs running on DVN01 and DVN02. So these are the other type of nodes I mentioned, the data analysis nodes. You'll also sometimes hear them being called the serial nodes. You can see that here in the partition name. And you might also hear them being called DVNs. So they are called either data analysis nodes or data visualization nodes. But they all refer to the same thing. So these are the type of job that we're going to run in an hour or so, less. I'll show you one running here in less time than that. And that's because these nodes are where we would do things like run Python scripts to process data, make plots, check numbers. There's a difference in the use case here. People running jobs on, let me see if I can find any, on the standard nodes, so these are the standard compute nodes, or on the high memory compute nodes, will be doing big simulations which need probably multiples of 128 processor cores at a time to do work. People running things on the data visualization or data analysis nodes in the serial partition will be using a single processor core to just run a Python script, say, or maybe run an R script or run something comparatively lightweight. So that's what the difference is there. So that command SQ, again, that lists everything that's happening on the system at the moment. The reason it's called SQ is, well, we're looking at the current queue, all of the jobs which are either running or pending on the system at the moment. And the reason it begins with S is because the specific piece of software, of scheduler software that we're using, is called Slurm, which is kind of a funny name, but there we go. It's what is it? Simple Linux Utility for Resource Management is, I think, what that stands for. And it has a whole set of commands, and they all begin with S. So this is another one. Sinfo tells us the status of all of the nodes on the system at the moment. So we can see lists of all the nodes, which type of node they are. So the standard compute nodes, the high memory nodes, and the serial data analysis nodes. And we can see what status they're in, what they're doing. But there are a whole load of Slurm commands. You don't need to worry about almost all of them. But just something to remember is that they all begin with S. So when we ran SQ like this, that showed us every single job running on the system. We can narrow that down to look at jobs belonging to a single user. So I'm just going to pick on someone here. Here's one user. So we can see every single job that this user is running by running a command like that. So just SQ followed by -u and then the name. You don't even have to have a space there. So just SQ, U, and name, and you can do that with yourself as well. So this is where it's most useful when you want to see what jobs you have running or waiting to run. You can see I've got nothing at all. Another command, which is a little bit easier, is SQ-me. That will run again and show a completely empty list of all the jobs I have running because I haven't sent anything off to be run. So there are two things to remember here. One is what a job is. A job is a request that you as a user, that I as a user am going to show you in just a second, that we send into the scheduler to say, I would like some quantity of resources to do work. If you're running on the standard partition or the high mem partition, so with the compute nodes as we call them, these big nodes which are just used to run large simulations, we would be asking for entire nodes. We'd say, give me 1 node, give me 2 nodes, give me 8, give me 64, give me 512 nodes. Remember, each of those nodes has 128 cores, so we're asking for a lot of computing power if we do that. At the same time, if I wanted to run a Python script, say, to read in some data into a Pandas data frame, which maybe sounds familiar, and do some work with that, get some interesting stats out from it, make a plot perhaps, that doesn't need all of that power. That just needs a single core. It doesn't need 128 cores. It certainly doesn't need tens or hundreds of thousands of cores. It just needs a single core to crunch those numbers and make a plot. So we would submit a job to the serial partition saying, I want to run a job on the data analysis nodes or the data visualization nodes. I would like a single core, and I want to run a Python script for, let's say, at most an hour. That's what a job is. And we can set up a whole array of jobs to do this. We could send off, I'm not sure what the limits are offhand, but you can submit a good number, tens at least, of jobs at once into the queue, and they will wait there. And what the scheduler, Slurm, will do is it will accept all of the users on the system. It will accept all of the jobs that the users on the system are giving to it. As I said, there's something like 4,000 users on ARCHER2. All of them are submitting jobs constantly, and at any time, you essentially can't run everything. So what it does is it sets up a queue. It works out what's going to run when. It takes this job is asking for 128 compute nodes. Another job is asking for 1,024. When do they run? In what order? Does any job have to wait for another job to finish before the nodes available for that are there to use? So that's why when we saw this output from SQ, there are some pending and there are some running. As the ones which are running finish, the ones which are pending are going to start. There's an algorithm called the backfill algorithm that Slurm uses to determine what the order of jobs is going to be. That basically tries to keep it as fair as possible. The idea is, if a job is reasonable, and if the resources it's asking for are there, it will run eventually. It's up to Slurm, the scheduler, to work out when it's fair for that to happen and to then start it. And when a job does start, it says, okay, job whatever number, it's your turn. You asked for maybe 8 compute nodes, or perhaps you asked for 1 core on a data analysis node. That's now yours. Here it is, and it starts running the job. And then that job will begin, and the work that you told it to do will execute. And assuming everything in your job is, set up correctly, it will start Python, it will start another executable, whatever you say it should do. It will read in its input data, it will start crunching numbers, and then it will end. At that point, you can log back into ARCHER2, you'll show up on one of the login nodes, and you can navigate to wherever on the work file system you set up your job, and you should see some indication that it ran successfully, whether that's just output saying, ran okay, or you've got new output files that you can take a look at and examine. Okay. For some of you, that'll be completely new. For some of you, that'll be old stuff you already know everything about. Before I carry on, is everyone happy with the concept of the scheduler and the queue here? Or does anyone have any questions? Okay, I think we're okay. Unless anyone jumps in the next few seconds. Okay, great. I think everyone's happy. So with that then, now we understand what the scheduler is, what it does, what these jobs are. Let's understand how we can actually set up a job, because this is now what we actually want to do. We want to write a job to do work. We want to start something happening on one of the data one of the data analysis nodes that's going to run Python, and it's going to run a script that we write to process some data, maybe make a nice plot. Who knows? That's what we want to understand now. So, so I think what I'm going to do is, this is where I'm going to inflict you all with every text editor that we have on Python. So, so I'm here at the moment, you can see anyway. This is my work directory that we saw from before. If I do ls-a, you can see I've got this directory test Python, which I'm going to ignore. There's also my .local directory, which is where I installed my custom Python packages on top of the central version of Python, CrayPython. Let's see how I would set up a job. So the first thing to do is to kind of think how you're going to keep your workspace organized. So let's do something very simple. We're just going to say, I'm planning here on running some very small example job, and I'm actually just going to run a hello world program. Remember, in Python, a hello world just looks something like this. It's just a hello world in speech marks or apostrophes in brackets, print, and that just prints hello world to the output. That's all I want my program to do. So I want to run a job that does that, which is kind of a waste almost, but it's about as simple an example can get. But I'm going to make sure that this is, fairly sensible on the file system. So I'm going to make a directory, and I'm just going to call it hello test, or I'll just call it hello world. Why not? Hello world. So there's my directory. So I've now created in my work directory a hello world directory, and that's where I'm going to set up and run my job. So I'll cd into there. Now the first thing I want is a Python script that actually runs hello world. So let me just very quickly, I'll use nano first, and I'll set up a Python script, and I'll just call it hello world.py. So using nano. So if you have never used a command line text editor before, this is about the simplest one you can use. I think from the poll everyone showed some level of familiarity here, but this is the easiest one to get going with, mainly because it tells you all of the options at the bottom. So it's impossible to get lost, which you can do with Emacs and Vi. So here I am in Nano. I'm working on a file which I'm calling helloworld.py. So this is a little different from the Jupyter notebooks which we were working in before. Remember, that was a sort of interactive document almost, wasn't it? I'd say a Python notebook sort of documents your work as you go. A Python script is just a set of Python commands, one after another, that are to be run one after another as each line is fed through the Python interpreter. So if I write a single line piece of code, this is just going to do print hello world. So this Python script does nothing but print hello world. And I'll save that, and I do that by, you can see at the bottom, pressing this circumflex here means press Control. So Control and O writes out. So I press that, and then it tells me to enter the name to write to, because I created it as hello world.py. That will show up by default, and I can press enter to save that. and then I'll press Control and X to exit. And if I ls now, I'll have hello world.py, and I can use cat hello world.py, and we'll see what's in it. Or I can use, less or more hello world.py, whatever you like to use there. How do I run a Python script? Well, you just do Python followed by the name of the script. So Python hello world.py, and that runs. Inside that script, I could have done anything more complex that I needed. I'll show you a slightly more complex one after this one, but just want to make sure we've got at least this example down before we move on. So there is the simplest possible, really, Python script, and it does nothing but print out hello world. Now, let's imagine that this script was actually doing something useful. And let's imagine that we wanted to run it on the ARCHER2 data analysis nodes. Obviously, there's no actual need to do this. We can just run it here like that, and it's done in half a second. And even for the examples we're doing here today, it doesn't entirely make sense. As Juan said yesterday afternoon, all of the work we've been doing in this course have really been toy examples. But let's imagine, if you like, that the script we're running maybe needs a huge amount of memory. So on the data analysis nodes, you can ask for hundreds of gigabytes of memory to use, because maybe you just need that much memory to actually store your data. Or perhaps it's going to take 24 hours. You can leave something running on your laptop for 24 hours, but well, it's a lot more convenient to run it as a job. So we're going to bear in mind that at the moment, this script, hello world, is actually not useful in the slightest. But if it were useful and we wanted to run it on the ARCHER2 data analysis nodes, we would submit it as a job. How do we run a job? Well, we need to write, you can do it another way, but almost all the time, you would write what's called a job script. And the job script is just another text file that contains a set of options to Slurm that tell it what resources you want and for how long, and then a second part that tells it how to run the job. So I'm going to use Emacs for this, and hope I don't regret anything because I'm a bit out of practice with Emacs. And I'll show you what goes into a Slurm job script to run our hello world Python script on the data analysis nodes. So here I'm just doing Emacs, my text editor, and you can call your job scripts really whatever you like. I personally like to give them a name that ends with .slurm, like this, just so that if I'm in a directory and I don't know what I called my job scripts, I can just do ls*.slurm, and I immediately, in this case there isn't one, but I would immediately go, yep, that was my job script. So I'm just going to call my job script submit.slurm, and now we've got Emacs open. So I'll run through this line by line, but I'll give you a link to the web page where there's the full example that you can essentially copy and paste almost. So first line of a job script is actually what's called a shebang. And you may sometimes see these in similar form at the top of a Python script. A shebang is a special command that essentially tells the script that's running this script what interpreter to put it through. So in this case, this is saying it's a oh, you've got an interesting error there. glib.gio message using the memory settings. It looks like a warning alone. Oh, sure. No. I'm showing Emacs here, but you can do this with whatever you want. I'm just sort of, I guess, showing some what shall I say, text editor agnosticism, I suppose. Oops, no. Yeah, so as Fran said, any editor should work fine. This is just a text file. You can write it whatever way you prefer. I personally would be using Vim here as my text editor of choice, but whatever works for each of you individually, go ahead and use it. Anyway, okay, so it starts with a shebang, which is just a way of saying how should this script be run, and it's ultimately a bash script, as we'll see. There are going to be bash commands that we want to run down below. Then we've got some special commands. These begin with a hash sign, hash sbatch. And these are special options which go to Slurm. So when we submit this job script, we'll see that we use another program called sbatch. And when sbatch reads this file, it sees these hash sbatch lines and realizes that these are options to Slurm. So up here, we're going to set some options for our job. So remember how I said each job in the queue we saw had a name? We can just call this Hello Python, for example. And if I can see this in the queue, if it doesn't run too quickly, I'll see that this is the name it has. So that's our first option. We also should provide a maximum time. So when we ask for resources, when we say I want a node or I want a core, whatever we're asking for, it's often a good idea to tell it how long is the maximum time it can run for. I think if you don't enter this, I think it defaults to, it's either an hour or 20 minutes, I can't remember. It does have a default, but it's always better to set it yourself. So this is the maximum time it can run for. I'm going to say it can run for at most, let's say a minute. So this is just hours, minutes, and seconds. You can add days if you want, and if the scheduler will allow you, you could do say 1 day and 1 minute like that. Personally, I just always give it in hours. So if I were running for 2 days, I would put in 48 hours, for example. In this case, I want it to run for 1 minute only. Yes, and you can skip zeros if you like. So I'm going to say, however, whatever my job is doing, it's going to run for 1 minute at most. If it finishes before 1 minute, great, it'll just exit and that'll be that. If it's still running at 1 minute, the scheduler, Slurm, is just going to kill it. So it probably won't be a nice exit to the program if it's still running at that point. So it's up to you to say how long is the maximum runtime. You might ask, well, why don't I just set it to run for 24 hours then? Because then if it takes 1 minute, it's fine. If it takes 2 hours, it'll be fine. The reason is, remember, everyone else also wants to use the system. If you give it a runtime of 1 minute, then that means that the scheduler is able to slot this job into any 1 minute gap that it can find, and it will start running probably very quickly. If we wanted it to run for longer, then we would have to give it a longer maximum time to make sure it did reach the end of the calculations. But the scheduler would then have a harder job in finding a gap for it to fit into. So 1 minute in this case is fine because our script is printing out hello world. It'll finish almost instantly, a couple of seconds to start up, a fraction of a second to print out hello world, and then it's done. Now, I'm going to run this specifically on the data analysis nodes. We're just going to focus entirely on the data analysis nodes today. We won't bother running at all on the compute nodes. So this is a little different, but what we're going to do is we're going to ask for this parameter here, ntasks equals 1. In Slurm, SBatch speak, if you like, this is asking for us to have a single processor core. If we wanted, we could ask for more. We could ask for up to 128. I believe it, we could anyway, but we could certainly ask for 2, 4, 6 if we wanted. And what Slurm would then do is it would, when our job is running, keep this many cores on the data analysis node reserved for this job to run. So the data analysis node, remember, has 128 cores. So when this job is running, Slurm is going to take one of those physical cores on the machine and say that that CPU core, that single CPU core, is reserved for this job to run. Nothing else is able to use that one core. So ntasks1 means we just want a single CPU core to work with. We've got another set of options now where we're going to say what type of machine, what type of node we want to run on. So if you remember, I mentioned that the data analysis or data visualization nodes are sometimes also called the serial nodes. Well, the partition, which describes that group of nodes, is called serial. So if we do SBatch partition serial, that means we're saying the node that we want to work on is a data analysis node. At the same time, we have to give it what's called a QoS option, which is also serial. QoS stands for quality of service. You can kind of think of it as a queue, sort of, in the sense of people lining up, or the job queue. But it's a little more abstract than that. It's sort of the terms under which the job is working. So I guess the main example is that if you were running on the compute nodes, you might be submitting to the standard QoS, in which case you would be limited to your job running for 24 hours at max only. But you could also submit your job to the long QoS, in which case your time limit is, I believe, 48 hours, but you can run fewer jobs. So there are a few options going on here. Thus, running on the data analysis nodes, it's simple. We just go serial, serial, and this together means we just want to run a standard job on the data analysis nodes. We need to do one other thing here, actually a couple of other things, sorry. One is to set the account, and this is how the job is charged. So here I'm going to use TA014. If we were running jobs in the compute nodes again, if we were doing some really big simulations, we would be using some number of compute nodes for some number of hours to do that. And when we do that, we have a budget which is charged. Each project has some number of compute units, as they're called, CUs. And when a job is run, the number of nodes is multiplied by the length of the job in hours, and that tells you how many CUs were used to run the job, and that is deducted from your balance. And that's to make sure that you sort of essentially can't run jobs forever. Most people using ARCHER2 have been given specific quantities of CUs to use, so they have a resource budget. They wrote some sort of application through one of a number of mechanisms to get time on ARCHER2, but they specifically said, I want to run jobs that total, let's say 10,000 CUs, which means 10,000 node hours, or which could be 10,000 nodes for 1 hour, or one node for 10,000 hours, just the number of nodes multiplied by the runtime. And every time that you run a job on the compute nodes, you charge your budget according to how long it ran and how many nodes it used. It's again a little different for us on the serial the serial data analysis nodes, because these are free to use. These are quite, low impact, I suppose. So these are free to use, but it's still information that we should provide. There's one final option here that we want to give, and that's mem equals something in gigabytes. I'm just going to use 2 gigabytes, but we could probably get away with 1 or 4. The node as a whole has up to 512 gigabytes available. I've read that it's 125 gigabytes, the maximum that we can ask for here. I'm not entirely certain on that, but at least we don't need that for now. We can just use 2 gigabytes, say. So this is much more important. This and our end tasks, these 2 lines together are saying that, well, actually in this one as well, these 3 lines are saying that we want to take 1 core on the data analysis node and 2 gigabytes of the memory, and we want those to be reserved for this job specifically for 1 minute at most. If we wanted, we can do more. We can ask for, again, we could ask for 16 tasks, and I don't know, let's just say 64 gigabytes of memory. And maybe we would want it for, let's say, I don't know, 4 hours. This is how we ask for the resources that we need to complete the work that we want to do. And if you're doing something really heavy, you might need more memory than this, or you might need more tasks. If you're trying something in parallel and you might need more time, you might want to run for a whole day to complete this work, perhaps. It depends on what you need to do, but you can hopefully see here how this resource is actually useful, because this is probably at the moment not something you can do on a laptop. You might have a workstation perhaps which can do this, but it's possible for this to maybe even reach beyond any workstation that you have access to. And the advantage as well is that this is automated. Once we submit the job, we can log out and we can go home, we can go for a walk, we can do whatever. Once the job is in the queue, the scheduler will take care of it. So I'm going to move that back to the original settings where I had 1 task for 1 minute and 2 gigabytes of memory. And that is essentially all of the Slurm options done. So we've given our job a name, a time limit, number of tasks, memory, what account it's running under, which is just our project code for the course. And then we're saying, and this is to happen on the data analysis nodes. Then after that, it's really now bash scripting. We want to tell it how to run our Hello World program. And I'm just going to keep this as simple as possible now. We're going to module load, cray Python. We don't actually need to do this because this is doing nothing except printing Hello World. But I'm going to run it in the version of Python that Cray provided on the system anyway. And then remember to run the script, Python hello, was it underscore? I think it was underscore world.py. And I'll just save that and exit. I believe it was hello, it was hello-py. Okay. So let me just replace that with a dash, hello-world.py. Now, I'm probably, oops, see, I keep on defaulting to Vim, even though I'm not using Vim. Okay, there we go, I've saved that. Okay, so that now should be, except I will probably have made a mistake, given, live coding always goes wrong. That should be a working, pretty minimal job script to just run Hello World. How do I submit it? I'll sbatch that. So here's that sbatch command I mentioned. You just do sbatch and then the name of your job script, which was submit.slurm, I think I called it, didn't I? Yes. So I do sbatch space and then the name of the job script. And if I hit enter, I'll get a message. That's good. And if I sq me, I'll see, there we go. It's in the queue. There's the name that I gave it, hello-pi. There I am as the user. There it is running on the serial partition. It's running at the moment. It's at the time I ran sq-me. It had been running for 4 seconds and it's running on DVN01. So the first data visualization or data analysis node. If I run sq-me again, I should hopefully at this point have an empty queue, and I do, which means that probably that job finished. And now, so there's the saved format. We can forget about that. This is new. Slurm dash, and then this is the same job ID as the job 3403930.out. So what's happened here? Well, let's just take a look. I'll use I'll just cat it. No, I will use more. Let's just use more. Slurm, just to show the different tools available. If I do more and then that file, hello world. So what's happened is the job ran. It took those resources that I asked for in the job script, one CPU for 1 minute with 2 GB of memory, and it ran module load cray python, and then it did my python hello world.py. What is the output from python hello world.py? Hello world. So that ran and it produced this output. So this was running on that other node, DVN01. And when it produced this output, Slurm captured that output and put it into this file. And I can do that if I do, I'll use Vim now. I'll go for what I'm most comfortable with, hello world.py. I'll just add a new line and I'll do print and goodbye. And now I'll just try sbatching that job again, submit.slurm. So now that is putting the reservation in the queue. It'll probably start running straight away because the data visualization nodes are often pretty empty. It will start a job. So it's going to start running a bash shell on the node. In that bash shell, it runs module load cray python to load the Python up for use, and then it runs python hello world.py. I should now have 2 Slurm files. Here's another one, which is the job that I just submitted. And if I check that out, I've got what I did in the Python script. Okay, so very basically, that is how you run a job on the back end. Does anyone have any questions about any of this? Again, this could be very new, or you might already be super good at this. It doesn't matter either way. If you have any questions, please do let us know. Okay, seems okay. So now I'm going to quickly set up one more example. So I'm going to go back. I've just gone back to my work directory /work/ta104/ta104/ my username. I'm going to set up a very simple script now to actually read in one of those files and produce some, actual useful outputs rather than just hello world, because we did all this setting up with plot9 and the like. So let's see how we can actually make use of that. So I'm going to call this one, what will I call it? I'll just call it PD test. I'm being very imaginative with my names. So here's a new directory called PD test, Pandas test, and this is empty at the moment. And I'm just going to, I'll just call it PD test again, why not? Create a new script, new Python script. And in that, what will we do? We'll import, no, wait, sorry, there's something I want to do first. let's make that data available. So here's a command you can copy if you like, and it's going to go to work ta104/ta104/shared/data, and I'm going to copy that data directory into this directory. So there's data, and if I do ls data, you'll see there's all the files that we've been working with. So if you want, you can use this command. I'll just put that in the chat, and that copies all of the data directory into your current location. That dot at the end, the data space dot, means that we're copying data into dot, and dot, remember, in Linux always means the current working directory. So when I did cp-r, blah, 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 data here, that's copied that data directory to this location. Okay, great. So we've got the data directory ready. So I'm just going to create my pdtest.py script, and I'm going to import. This is just the same as we've been doing in the Jupyter notebook. We're going to start by importing pandas using the alias pd, just to make it a bit easier to work with. And then what will I do? Do surveys, df, wasn't it, equals, let me make sure. I'm just going to try to, bring up what we were doing previously so I can hopefully keep things consistent between what we were doing before and what we were doing now. Yeah, okay, so surveys df, let's call it, and that's just going to be pd and then read csv data/surveys.csv. If you do, if any of you see me making a mistake, please do yell out or use the chat, because there's a definite chance. And then after we've read that file, what will we do? Let's just, I don't know, let's just print surveys.df, surveys.df, sorry, surveys_df. See, I'm already making a mistake. And we'll describe, I don't know, the weight. I think that should be okay, shouldn't it? I can always check. So that's a super simple script. It's doing barely any work, but it should be enough to demonstrate what we're doing. And then I can do submit.slurm, which I'll create. And I'm going to use a slightly different script. So now I'm going to take, let me paste a link. So I've got in the web page, you can follow this link once I've grabbed it to get the complete job script that we'll be using. And you can essentially copy and paste this job script. That's what I'm going to do just now. You'll see it's essentially what we've just done with a few more parts. Everything up at the top is identical almost. What will I do? I'll change the name. So I'll call this, I don't know, data describe. It's going to run, well, I'll leave it at 20 minutes. So it obviously will take, 20 seconds or something instead to start up and then run, rather than 20 minutes. But that means it can potentially run for 20 minutes before it's forcibly shut down. And we're going to run on the serial partition and QoS with TA104. We'll limit ourselves to 2 GB of memory. We've got some extra commands just here. You don't really need to worry about this one too much. This is essentially, this is something which is just often beneficial to run. It makes sure that if there's anything in the background that's running which uses threading, that it's disabled just in case it starts to thread. If you don't know what that means, don't really worry about it. It's essentially a safeguard to make sure that nothing extra happens in the background that might impact the performance of whatever we're running. Then what we are doing the same is we're going to load CrayPython again. So once our bash shell starts running on our reservation on the data analysis node, it's going to run module load CrayPython, which makes CrayPython available. Great. Then, and this will look familiar, it's going to set up our extra bits that we added onto Python. So when we added, when we did the pip install user matplotlib plot9, we installed it in our work directories. This is the same commands all over again. This bit of script here just refers to our work directory and says that everything's found in the .local directory in our work directory, and then these are identical commands. So these lines here make those commands, make those extra bits of software usable within the job. And whenever we want to use that extra software which we've installed, we need to do this. Something else I guess maybe just to note, because I didn't do it in my first really simple script, I've got these other commands here, hash, make available user installed Python packages installed in work. These are just comments. So just like in Python, which I could have done in my actual script, anything beginning with a hash is a comment. It's something which is ignored by bash here. So just so that, you know, if you come back in, you know, half a year's time and look at it, you can understand what's going on. And then at the very end of it, I run finally Python. So what did I call it again? pdtest.py. So I'll just change this to pdtest.py. That's right. And again, you know, again, my pdtest.py, I could have, you know, put in some comments here if I wanted. Just to help myself when I come back in the future and don't have a clue what I was doing. And then with that all done, I should be in position. And again, it's important to note, let me just quickly show you pdtest.py. This says I want to read data/surveys.csv. Well, what do we have in the current directory? Data. What's in data? So surveys.csv. So that's fine. This is a relative path. It's saying from this directory where we're running pdtest.py, grab data/surveys.csv, and that's there. So with everything now in place, let's submit that job and hope I haven't made a terrible mistake. I can SQ myself again, and I can see there's my job running. It's got the new name I gave it. As I said, the data analysis nodes are often not, you know, they aren't full up with jobs. So often you can just start a job going and it can go straight away. And that has probably now finished. If I ls, well, there's my slurm out file. And if I check, there we go, it's run. So that Python script opened the file and printed the output of the .describe method on the weight column. So I think with that, we've kind of got everything that we need to at least submit jobs. There's maybe one more thing which is useful to know. Sometimes if you sometimes you might submit a job and maybe you decide you shouldn't have sent it off to run after all. Perhaps perhaps it's sitting there waiting in the queue, or it might be already running and you just change your mind, or you realize you did something wrong, or perhaps you want to change the input it's using to read in a different file, or perhaps sometimes it's already started running and you can see it there with the running status, and you check the output file. So if it's running, it will dump all of the output that it that it gets into this file as it runs. So you can check you can check your slurm.out file as it's running and see what's happening to your code. And if you see it's, maybe there's a bug in there, it's not doing what you thought it would. In all of these cases, you might want to just cancel the job. In that case, what you do is you get your job ID from SSQ. So in this case, 3403996 or 3966, and you run scancel and then give it the job ID. And you press enter, and I don't get anything. That has actually done nothing because the job finished. But if that job had been running, it would have cancelled it. If it had been pending, waiting to run, it would have just silently taken it out of the queue. So I think that is everything that we need to kind of get going with trying out some examples on ARCHER2. So, which examples do we have? Let's take a look. Which exercises? So, I think this might be a good thing to do. Let me bring over a Firefox window. Okay, so here's Firefox. Here was, so this was some of the very material I uncovered yesterday, starting with data. So this was just where we first started reading in data using Pandas. And then towards the end of it, we produced some plots. And at the very end, there was this summary plotting challenge, I think. So I guess this is our first exercise we can work through. So we're starting from here. We've just read in that surveys df is read in from data/surveys.csv. And then what we want to do is we want to produce a plot. Where is it now? Produce a stacked bar plot with weight on the y-axis and the stacked variable being sex. Let me make this bigger. Okay, that's maybe a bit easier to see. So we've got some tips below as well. So I think we could maybe say, how long do we have until our scheduled break? I've already lost. When were we scheduled to break? 3:15. I reckon we can maybe carry on until then. Let's try then and work for the next 20 minutes on this exercise. Let's see if we can write the code to do this, write a job script on ARCHER2, submit it to the queue, and run this on the ARCHER2 data analysis nodes to produce this plot. Oh, wait, there is something as we get going. One thing I maybe should show you is how to save a plot. Actually, did we cover how to save Pandas plots to file one? I can't remember if we did that yesterday or not.
Yes, it was covered. So
okay.
that was one of the suggestions that I think we can. The exercise that you suggest, I think we can do it on ARCHER2 and see how we can do it in a script. So I think it's a good suggestion.
Yeah, and we also covered earlier on today how to save the plots made with plot9. So I reckon we should be set. So so what we'll do is if we get working on that for the next 20 minutes, and then I can also show you how to view image files on ARCHER2, or else how to copy them back to your own machine to take a look. So I'll let you all get on with that. will be here. So please, again, either put questions in the chat or just unmute yourself, and we'll be here to help if you run into any problems. Hi everyone, so that's us 10 minutes in. I hope you feel you've been able to start getting somewhere. In 10 minutes time, so I think just as we head into the break, I'll quickly show you all how to set up at least what directories you might want, what files you need, and maybe the contents of the job script. And then we'll leave it for half an hour's break from 3:15 to 4:45, and you can carry on maybe working on your Python script if you still haven't got it then. And when we come back, I'll walk through the contents of that Python script as well, and we can see how it works. Until then, again, please shout if you need any help. Hi again, everyone. So we've got a couple of minutes left before the break. So just before we all head off for coffee or tea, or maybe both or neither, or whatever our preferences were from earlier, I just want to quickly show you what you maybe hopefully have in place. And then after we come back from the break, we'll quickly go over the solution, see if it's what you will manage to get. So you can carry on working on it if you want to. But what you hopefully have is, well, here's a directory I just created, starting with data. That was just the name of the section from the material. So this is where I'll be setting up my my work to do. So I'm just going to copy here my data in here. So I'll just copy the whole data directory in. You don't have to do this, and I think I'll actually show you how to do this without copying the data everywhere you go after the break when we're looking at the solution. But you need that data there. Then you also need your job script. So I'll just call it run.slurm. And where is it? I will just copy and paste across that job script that I linked to you from in the material. And I'll just set it up to run a Python script. So I'll insert this, and what will I call my job? I'll just call it, what will I call it? Stacked plot. Why not? Stacked plot. I'll give it, I don't know, 10 minutes. Still far too long. It doesn't need 10 minutes, certainly. It's running in serial on TA104, 2 GB of memory. That's perfect. This is all set up. And I'll just call my script, what will I call it? I'll just call it stacked plot, maybe stacked plot.py. So that's going to just settle that up. So at this point, I've got my data in place. I've got a job script ready to run. What I don't have is stacked plot.py. What goes in here is still a mystery. So if you're done, I'd say just take a break, go and get something nice to drink or check your emails or do whatever. But then otherwise, this is now a break, and we'll come back in half an hour's time at 3:45 when I'll show you the code that goes in here and how it runs and how we can check the output. And we'll move on to, well, at least one other example. If we can fit in 2 before the end of the day, that'll be great. But we'll go over this and at least one other more exercise. Okay, if you think you're done though, I guess you can pat yourselves on the back and go for a break. And I'll see you all again in half an hour. Again, I'll still be here, so please do let me know if you're having any issues with any of this. Okay, so welcome back everyone. I hope you were able to get something refreshing, keep you carrying on. Friday, I know Friday afternoons feel very slow to me, or otherwise carry on with the exercise if you weren't able to finish it. Now we're back though, let's take a look then at how we can actually run this piece of work, producing this stacked plot on the ARCHER2 backend using the data analysis nodes. So, so just to remind ourselves what we were trying to do, where's my, here it is. Just lost my Firefox window, there we go. This is what we were aiming to do. We were trying to create a stacked bar plot, just as we've been doing earlier on in that session, as Juan showed us yesterday, where we were stacking by the sex of the measurements and showing the total weight for each site. So we would have on the x-axis the different sites, the plot IDs, and on the x-axis, on the y-axis, the total weight, and with colors showing how much of that weight was coming from the two sexes. So that's what our goal was. So how would we do that? Here we are again. Here's my my example directory here, where I'm aiming to run this on ARCHER2 on the data analysis nodes. Oh, I've just got a message. Well, okay, that's no problem. Hope you've enjoyed it. I'll see if we can if I can hopefully demonstrate this through to the end at 4 p.m. maybe at least, and then maybe hopefully at least if you had any questions about this, you'll get answers, or at least have had an opportunity to think about it. Okay, great. So here is our my RADA directory. So maybe you've set up something similar in your own work directories. I've copied the data across, I've created my job script. All I'm missing is the actual Python to do the work. So I'm going to just open stackedplot.py, where I'm going to write this. So what are we going to do here? Well, first of all, we need to do one very important thing, and that's to import Pandas. And we're just going to give that the name of PD so we can make calls to it easily. What do we need to do? Well, we need to open that file, read it as a CSV file, and store the data in a data frame. So let's just use the same names that we've been using up until now. So we'll call it surveys.df, and we'll call PD read underscore CSV. And in this case, I can do data slash surveys.csv. And that alone would be enough to read that in and store it in surveys.df. I'm actually going to be a little bit more verbose here. I feel that because this is running non-interactively, it's nice to have something being printed out to into the file, into that slurm.out file. So I'm actually going to change it a little bit. I'm going to store the file that I'm opening in a variable. Remember, we can create these variables to store text. And then I'm just going to open it like this. So file name contains the file that we're going to work on, and then that's passed through to surveys.df to open. And I'm going to add a little bit of text here just to say what we're doing. So I'm going to say that opening file, and I'll just add file name, just so that there's some output in that slurm.out file that says what we're doing. So particularly if you're doing something that's really long running, something that maybe takes hours and hours to run, having something in there that you can just check on to see what's happening, I think is very beneficial. This is just super quick. I'm not making I'm not formatting it to look nice or anything. I just want something there. Just some text to say what's going on. So that should be enough code to open the file that's specified in the file name variable. So data/surveys.csv. Very quickly, I will actually show you one other thing here. We could do something else. So this is, remember, a relative path. I copied the data directory into this directory, but we could also give it an absolute path to the copy of it in the shared directory. So the original that we've been copying from. And that would then be surveys.csv. I'll leave that one like that, so we can actually see that working. I'll comment this one out, and remember, you can also always add comments to say, you know, to give you a hint in a few months or years' time what you were doing when you wrote this. Here it's fairly obvious, but it's always good practice to comment. Now we've got a little bit of work to do. So first thing we want to do, let's think about this in stages, is we want to group everything by site and by sex. So let's create a new data frame, which is the original but with groups. So we're going to call this surveys, surveys.df, and we're going to group this by both the plot ID, it's one thing, and the sex was the other thing. And now we've got a different way of viewing the records of all these animals that were in each of the sites. So there's one thing. Then we want to count the weight. We want to sum the weight in these categories, in these new groups that we've created. So let's say site sex count equals by site sex. And we specifically want to look at the weight column of that. So let's look at the weight column, and we specifically want to sum the weight column. So at this point, we've got a data frame where we've got sums of the weight for each given plot ID and sex. That's what we want. Remember, there's that little extra step that we need to go through. We need to unstack that. So we'll do site, sex, count, unstack, so that we move those sort of extra rows for each of the, so this will show for each plot both of the sexes, but we want to have the two sexes summed weight as new columns with plot ID. So we'll unstack them like so. And that's everything that we need to do to prepare the data to plot. Let's just add a little comment to that again. So we'll say we'll group the data by plot ID and sex, then sum the weight within the groups, and unstack. Should be, again, I'm not really, that isn't really necessary. I feel that the calls there kind of describe themselves, what they're doing. I'm just being very cautious here in how I'm commenting it. And I mean, again, as we've seen during, as Juan walked us through it all, we've seen that, you know, we can actually combine all these calls. So we could just do SPC if we wanted in a single line. If we wanted to do this, we could just go right back and do surveys, df, group by. Maybe I'll actually just copy and paste this to make it go a little faster. You can chain these commands one after another. So this would do the exact same thing in a single line. Some people might do it one way or might do it another way. Actually, that's not quite right, is it? There's a mistake there. Grouped by, and it should be this here instead. So you can see now each of those things happening. We take the original surveys.df, we group the data by plot ID and sex, then take the weight column, create a sum across the groups of the weight, and then unstack it. That's everything that we've done in these 3 lines in one single line. Certainly there's some brevity in this. I feel that the first 3 show a little more about what's going on here. Having these long chains of actions, I feel, is not quite so readable, but ultimately this is down to what you feel makes for readable code. Once that's done though, well, that's our data prepared. So let's just note that. Oops, again, still I cannot type. Let's make a plot. So everything's done. Let's create an S plot, let's call it. And so that's our sum plot. And we'll do spc.plot. And we want this to be kind equals bar. So bar plot. Remember where each of those bars shows us the total weight for each plot ID, and we're stacking the sex. So let's set also stacked equals true. Oops. Stacked equals true. And let's give it a title. And what were the units? Kilograms, were they? I imagine kilograms. And we can also set some labels on that. So we can do set X label. Don't really need that. And let's do splot.set Y label. And that's just going to be plot ID, isn't it? Now there's one other thing that we need to do. I'll just save that. And that's we want to save that plot to file. So when we were working in the Jupyter notebook, the plots just came up as part of the notebook as we worked our way through it, as we added new cells and entered commands. Now that we're running this as a script, that's different. We don't have a notebook for these plots to just show up in. So what we should do is we should save these to file. So I'll just add another print. Actually, let me just add another comment. Save to file and end. And then let's just do splot.figure.savefig. And we'll just call it, what will we do? Weight by site.png. That'll do the job for now. And then I'll finally just add a last line that will say done exiting. Good enough. Okay, so that should be our script. You've opened the file. We've opened the file. Well, we've imported pandas. We've opened the file and read it into a data frame, into a pandas data frame as from its CSV format. We've done some manipulation of the data to group it in this way by plot ID and sex, and to then sum the weight across those groups and unstack that to get it in the right format. Then we've created a plot where we're choosing to stack the bars, set some X labels and Y labels, and given the whole plot a title. And finally, we are saving to file. Hopefully I haven't made any errors here. We'll find out if I have in just a second. So that's now our Python script in place. Our job script to run, to reserve the resources for us on the back end, and to then run that script on the back end. because it ends with that Python stacked plot.py command. And if we were to use the data here, we would do, I'm just actually going to, let's just rn minus rf that data. So now my script is going to read the data from this shared location, which we all have access to. So with that, let me run that script, and it submitted it okay. I'll find out if there are any errors in it. Okay, that's running. So you can see there I was too quick here. The job was still pending. A second later, it was running. I check again. It's still running now, so it's definitely doing something more. What I can do is I can check that slurm.out file, and we can see there's the output. So opening file, there it is. It managed to open it fine, file open, did the work, saved it to file, exiting, and let's check. And there is weight by site .png. Now comes the question. We want to take a look at this plot, right? We can either copy it from ARCHER2 if we want, or we can take a look at it there. Now, something I found out, so there's a tool on ARCHER2 called Image Magic, and I found out about 25 minutes ago now that it doesn't have the ability to display PNG files. So what I'm going to do is I'm going to show you two things here. One, I'm going to show you how we can view it directly on ARCHER2. So for that, I'm going to open my Python script again, and I'm going to just rename that to to a JPEG. TIFF also works. Actually, yeah, why not? Let's just go a bit crazy. Let's just save it as a TIFF image file, and I'll submit that again, and then I'll show you how we can view that directly on ARCHER2. So that's running now, and if we do ls, we've now got two job scripts, and let's take a look at the newer one. Nothing's happening at the moment, and yeah, so you can see there's some overhead, there's some sort of spin up time. When the job gets going, it takes a little while for everything in your script perhaps to execute, in your job scripts to execute, for the resources to be allocated, and then finally for things to get running. There's a little bit of overhead in the job getting going, and then once it started running, it was over in an instant almost. But we should now have that TIFF as well. So how do we log into ARCHER2? Let me make this bigger again. Log into ARCHER2 with graphic forwarding enabled, so X11 forwarding. So I'm on a Mac, and I've got Xquartz installed. If you're on Linux, you've probably got X11 and or Wayland installed. And if you're on Windows, you should be able to go into your MobileX term session settings for the ARCHER2 connection, go to advanced SSH settings, and there should be a tick box to let you enable X11 forwarding, and you need to do that. And for me to log in, well, I'll just show you what I do. I would just do WLTA 104 at login.archer2.mac.uk, and you can give it this -x option. You can also do -y, but it's a little less secure. I'm never entirely certain of the distinction between them, but I believe X is preferable if it does run. So SSH, there's my login at login.archer2.ac.uk-x. That enables graphical forwarding. And then I'll just need to grab my password quickly from my password manager, because there's no way I can remember it. Okay, I think that's it. And then I'll log in. So here I am again on ARCHER2, and I'm just going to do module load image magic. You'll see it's the magic with a K. They make it sound very old-fashioned. Image magic with a K. You do that, and now I'll just head over to my work directory. If I can get there, TA104/TA104/WL. There I am, and I was in exercises and starting. Oops, I totally ruined that by going back to my home directory, and then into starting with data. And here I am again. Now that I've loaded the image magic module, this means I've now got extra software loaded and available to use from the image magic package, and one of those is called display. You can just do wait by site.tiff, and if I did this with the PNG, that would fail. With the TIFF, it should work. In just a second, a window will open for me, and I might need to drag it over to this screen. Yep, here we go. It's just opened up. This is the window that's just opened for me. So this is now Image Magic's display program on ARCHER2 running and showing me that wait by site.tiff. And you can see here are, oops, I named that wrong, didn't I? This is plot. I did the X and Y labels the wrong way around. I can fix that quickly. So X label should be plot ID and Y label should be weight kilograms. So yeah, this would be when I would be glad to have a debug run first before maybe wasting hours and hours producing a plot with incorrect labels, which would be a bit embarrassing. But fundamentally, the data being shown is correct. We've got our summed weight for each of the plot sites, and that's a stacked bar plot where we can see in each site how much of that contribution to the total weight is coming from female and male. The other thing to do would be to just copy that file from ARCHER2 to your own machine. And to do that, I'll just log out. I would do SCP WLTA104. I'll just use SCP. Login.archer2.ac.uk, and well, I need the path, which is this. I'm not sure why I PWD'd it when it's in the prompt anyway, and the file name, and let's just grab the PNG, why not? And I'll save it into my downloads directory. So this is now, you can see from the prompt, this is me on my MacBook, and I'm SCPing. There's my login. So this is me SCPing something from ARCHER2, and I'm specifically copying weight by site.png in my directory there, and I'm copying that into downloads. And if I just run that, I'll need my password once more, which is annoying because I just closed my password. I'll just grab it again quickly. And then we should see that being copied across to, there we go, that's downloaded, and I can just now, show you again a plot that I've now opened in preview locally with incorrect axis labeling. But those are the two ways to do it. Ultimately, everything that you create on ARCHER2 or any remote system that you're working on, you'll need to copy back, whether that's with SCP, which is good for just small things like this, or rsync, which you can use to move entire hierarchies of directories and data back and forth while keeping their archival properties intact. Or maybe you would zip things or tar things up first before doing so. And of course, if you're using MobileXterm on Windows, you've got that GUI there on the side that you can use to browse around and just drag and drop files back and forth between ARCHER2 and your own machine. Okay, so how did everyone find that? Did people come to similar methods of doing that? Did anyone do anything differently? It would be maybe the most interesting thing to ask. Maybe you got the axes correct where I didn't. That would be a good thing to do differently. And of course, if you found any of this problematic, we're kind of going through several layers of difficulty here. We're working with this data remotely, so we're having to write the job script to do it all remotely, and then we're having to run it through a job script to run the Python script on the data analysis node. So I would say it would be completely understandable if anyone found this difficult, because I'd say, well, it is. Okay, I think everyone seems to be happy with what we've just covered then. Is there anything else from this just now? I don't believe so. I think we've gone through this example fairly well. Ultimately, everything that you were to do would follow some sort of workflow like this. You would get onto ARCHER2. You would set up your directories on the work file system to store your data and to create your Python job scripts or whatever other scripts are, or if you're compiling some programs out of C or Fortran or C++, you would get everything that's needed to create or process data in place on the file system, and then write a job script that says, I want these resources for this long. When the job runs, execute these commands, and then you send that off into the queue, which the scheduler is taking care of. And when the time is right, the scheduler will then execute that. So again, this example, this exercise and any others, and again, they are toys. You saw it took a fraction of a second for the actual process of opening the file, working on the data, and then saving a figure, saving a plot from it to happen. This took a fraction of a second once this began. So as it is, there is no need at all for us to actually do this work on the ARCHER2 data analysis nodes. The situation is completely different if you were to be processing a huge amount of data, maybe hundreds of gigabytes all at once, which you maybe wouldn't be able to get into memory on your laptop or workstation. You would need something like this to just store all that data in memory, or else something which is going to take a long time to run. Again, if you were doing some very intensive post-processing of data that takes hours and hours, 24 hours perhaps or longer, you would want to use something like this where you can schedule perhaps multiple jobs. You could have multiple jobs in the queue to take 24 hours each to run, and you would be able to submit those, today, end of the day on Friday, 4 o'clock, just gone 4 o'clock on Friday afternoon. You would be able to send all those jobs into the queue, and then do something else, do other work, go home, whatever, and perhaps come back on Monday to find that they ran, from Saturday night through to Sunday night and completed. So that's where the advantage of a system like this comes in. It gets you automated, non-interactive work done using potentially a lot of compute power and storage and memory to do this. Okay, so I hope with that exercise in place and some tests done. You've had a taste of this. So I guess at this point, at 4:15, what I'll do is I'll run a poll, and we can maybe see what people would like to do now. So there are some other exercises. And we could either do one of those, or given it is now 4:15, maybe you would like to just call it a day and either head home or head off to do something else before heading home. I'll just create a quick poll, and then we'll see what those of you who are here would like to do. We've already had some people leaving for the afternoon. Let's see, so an exercise on maybe on plot 9 we could do. Obviously we've just got a message. I'll just be there in a second. Or we could do an exercise on processing data in loops. Or we could do maybe an exercise on merging data frames, perhaps. Okay, so I'll start that poll. So please, this is anonymous, so to each other, you don't have to worry about knowing what each other's saying. Okay, so I think there's definitely appetite to keep on running things, so we'll do something else. I'm happy to stay on until 5 o'clock, and so is Juan if anyone needs any help. Okay, so some people would like to call it a day, and at least one person would like to try an exercise on using plot 9. I'll say I will keep on going. We'll keep on going until 5 o'clock. Those of you who would like to leave, thank you for coming. I think both Juan and I have enjoyed, us running this. I hope you've enjoyed being on this course. I hope you've learnt a good amount from us. I think you should be receiving emails within a week or two, certainly, asking for feedback on this course. This is the first run of this course that we've done. So please do let us know how this course went for you, and if there's anything you particularly liked or didn't like, any changes you would like to see made to it that you think would have made it a more useful course. That would be very, very useful for us, so that we can carry on improving this for any future runs that we do of it. That would be very much appreciated. But yes, so if any of you would like to leave, thanks very much for coming. Hope you've enjoyed things, hope you've learnt a lot, and well, I hope you enjoy the rest of Friday and have a good weekend. Okay, for those of you who are staying, let's see. Oh, we've had some changes. Exercise and processing data in loops. Oh, well, let's see then. I think what we could probably do, if that's only going to be 2 of you running these, I reckon we can show you quickly what's going on for each of these exercises, and you can try both of them, and we can, help you with whatever issues seem to come up. So I believe we've just had another question as well. In general, after the course, can we still use? So I believe you should. Juan will know for sure. I believe you have. I believe you'll have access to ARCHER2 for a month still after today, when you can carry on using it, working on the material that we've just covered. If you have access to ARCHER2, otherwise, through a project that you're a member of, that would probably be very helpful. But really, a lot of what we've covered here can be taken, certainly the Python material can be taken anywhere. You can run that type of code anywhere where Python is running, as long as you've got those packages installed. But certainly the material I've covered on using ARCHER2 is 100% useful for using ARCHER2, and a lot of it will be transferable elsewhere as well. Really, most clusters operate in a similar fashion. So the idea of having a scheduler to run jobs for people remotely, non-interactively, is the default way of using supercomputer clusters. So whether you're using ARCHER2 or any other cluster, chances are you'll be working in a very similar workflow to this. Okay, thanks. Thanks. I can see some thanks coming through in the chat. I'll say thank you for coming. I'm very happy to have been here, to have been of help to you all. So yeah, it's been a pleasure. I hope you've enjoyed things. Okay, so so some people are staying for at least a little bit. So so let's stop that poll. And let's see. So the two. Let me bring across my browser window again, so we can. I'll zoom in so that's visible for you. So the two exercises that people were interested in. So so one was on data workflows and automation, I believe, in here. Yes. So this is what you might want to look at. Sorry, I can't remember who said they were interested in which, but for the people who are interested in looking at, where is it? Yes, so yes, this is what we wanted. Writing unique file names. So this is a little bit of what I was showing in the code I was just writing. So this is in session 7, data workflows and automation. So what you can do is you can, and I've already lost my place in here, haven't I? So a little bit more than half out. Writing unique file names. You can try to take this exercise and run through this challenge here. So up above, you'll be taking the original surveys DF, reading that in through Pandas, and if you remember, there was a year column. So that file, surveys.csv, contained everything across all of those years. But what you could do is you could take just the data for one particular year. So in this example, we're taking just the data for the year 2002, and saving that to its own CSV file. What would you do if you, say, wanted to create a new file which contains only the data for one particular year? Well, you could run a for loop through all of the years, all of the unique years given within that column of the data frame, and decide on a file name that would store that data. You do that with a for loop like this. So for each year, so for each numbered year in the file, determine a new file name, and then this loop is just printing out the file name. So this is everything you'd get. And what you could then do is write to that file. So you could select just the data from that data frame for that year, and then save it to a file with that file name. And so every file has a unique name, which is given by just storing it in that variable. The first part just contains a path. So now we're saying within the data directory, there's a yearly files directory. And then within that, there's a file which begins surveys, is then followed by the string conversion of the year. Remember that the year is an integer number. This will convert that to a string and then append it. It will concatenate it onto the end of this string. And then it will finally concatenate it again with the .csv suffix extension. And so you'll get files like yearly files, surveys 2002.csv. So what you can do is work through this challenge. So just as I've shown you now, creating that stacked bar plot, you can log on to ARCHER2 if you aren't at the moment, and you can try to set this up to save the files for all of these years, working through the problems as they are here. So you'll see that some of them are NaN. So there's a problem there. So first of all, let's make sure that we don't include the NaN files. How would you then maybe change the loop so that you're only outputting the data for every 5th year, say? And then you can take it even further. How would you split it up so that there are files not for every year, but for every species? So this is going to be a way of an exercise of changing how this loop is structured and what you're doing inside the loop. So I would log on to ARCHER2, go over to the work file system, set up a new working directory for this, try and take this code, do what you think needs to be done to fix it according to this challenge here, write a job script for it, and see if you can get it to run. And I think I heard some comments possibly coming through. Someone else has run out of mental bandwidth. That's completely understandable. 4:30 on a Friday afternoon, everyone is. Well, I certainly have no mental bandwidth left, I feel. Okay, so that's one of the challenges. And the other one that got a vote was, yes, plot 9, because couldn't do any yesterday. Okay, so anyone who wants to look at plot 9, so there's a very generic challenge, I feel, at the end here, which is to customize the plots and essentially make them look nicer. So you can see if you can change the width of the lines, because there are some line plots generated up here. Maybe see if you can make those wider. Maybe you can change the style of them so they aren't solid lines, they're dashed lines or dotted lines. Maybe change the name of the legend or the labels, and switch to using a different color palette. Just in general, what you can do is essentially take what we're doing here. You should ignore the matplotlib inline command that's specific for Jupyter to make sure that the plots show up in Jupyter as you work through. You'd maybe write a script. In fact, maybe I'll show you. Let me see if I can quickly set this up. What's it might look like. Should be able to. Oh, of course, I'm doing that, aren't I? Yes. I want to go half and half here. So I'll show you maybe what you would be doing if you were working with plot9. So assuming you've got plot9 installed, I'll just through pip and ARCHER2, I'll just do a make dir plotline exercise, and I'll cd into plot9 exercise. What you would be aiming to do would be something like the following. You would say vim, again, just my text editor of choice. What would I call it? What's the first plot that we make? Hind foot versus weight. Sure. I'll just call it HF versus weight. Why not? .pi. And you would just be doing the following. So you can see the first thing that's needed is to import plot9 as p9. Okay, so that's us with plot9 in place. We can alias it through p9. We'll then do the same. We'll get pandas imported as pd. Then we'll read in, I'll just copy and paste this actually. So you can see that the actual Python code is completely unchanged from what we were doing when we were using a Jupyter notebook. The only difference is that that was a responsive, interactive way of coding in Python. You entered your bit of script and you hit Shift Enter, and the Python interpreter ran that line or those lines, and if it produced a plot, the plot popped up below it. Now that we're working non-interactively, we're running a Python script, and that's running on the ARCHER2 backend on the data analysis node. We're not going to see any of that happening. We have to write the complete script from beginning to end in one file, and then say that when the job runs, we want Python to run that script. So I'll just change this again so that it's going to read the shared copies of the input data. So I'll call it TA104 / shared. That's wrong. So work TA104. Yes, yes. And then the shared directory data / surveys.csv. And then what do we need to do after that? Well, let's just go straight down to the, oops, this is going backwards and forwards a bit, isn't it? To the script here, and that's that. So we create surveys plot. This formatting is not very nice here, is it? Just about makes sense. Can I drag that over a bit? That's a little bit better. That is going to say run p9.ggplot, and that's going to take as the data, the survey's complete data frame, which we created above and dropped all of the nouns from. And for a mapping, for the plot, we're going to set the x-axis to the weight and the y-axis to hind foot length. And then finally, we're going to draw that as a, we're going to draw that with a geom point. I'm actually not entirely certain that this will run as is. I'm going to say, let's do this instead. I think this is better. I'm going to delete these lines. I'm just going to create surveys plot. Oops. So I'm going to say surveys plot equals all of that. And then what is it? Save fig. I was trying to say I'm the same. I cannot remember the API. How do you save them? I can't remember. myplots.save. So we're basically doing this. Well, in fact, in that case, let me just copy all of this just to make it quicker. And please feel free to fix that formatting because that looks terrible, doesn't it? It's just about okay. So this is going to then, so first of all, import our packages, then read the CSV file using this absolute path that starts with a /, so it's starting at the root directory of the file system, starting in / going into the work file system, then going through TA104 shared data surveys.csv and dropping that into the surveys complete data frame. Then from that data frame, we drop the nans because we don't want to deal with not a numbers. And then we're going to create the plot. We're saying that my plot is equal to all of this, everything between this opening bracket and this closing bracket, where we create a p9.ggplot, ggplot from R, and we're using surveys complete as the data again, and we're mapping weight on X with Y as the hind foot length, and we're plotting that with point geometry. So this is going to be a scatter plot because of this line here. And then finally, with the myplot object, as it's called in existence, we refer to it and say that we want to save it into scatterplot.png, which has width 10, height 10, and DPI 300. So if I exit that and save, that should be a working script, I hope. We will find out, of course. What's left then is to write a job script to run it on the back end. Again, if you just take the job script from the material from this afternoon, do I have that in a handy window somewhere? Yes, I do. Here's the material from this afternoon. This job script is here. All you would really need to do is change the name of the Python script. Then put this into a text file in that same directory again, alongside hf versus weight.py. So maybe I'll even just do that quickly, show you that's working, and then you can go away and try the other exercises, the other challenges on this page. See, what changes you can make to those plots. Can you get them to run? So let me just create run. I'll just call it run hf versus weight.slurm. Just say, again, the name of your job scripts can really be whatever you want. I will change it to give it a proper name. I'll call it hf versus weight. And what was it? It was just hf versus weight.py, wasn't it? I think. And hopefully I've not made any mistakes. And if I sbatch that, that will be sent off to the queue to run on the data analysis nodes. It's pending. Now it's running. We'll see in a second a slurm.out file appear, I hope. Still running. Oh yes, remember it took plots9 forever to be imported, so this might take a little while to run. Still running. At least we've got our slurm.out file. Anything in that? So something else I'll note, if you see any errors, so if we had made a mistake in our in our Python script, we would see the error output here. Maybe I'll quickly show that actually once we see that this is run. Okay, so these aren't errors, but these are warnings. I think we saw Juan getting these warnings when you made these plots yesterday. Yeah, saving 10 by 10 an image. Yeah, so when we ran this, maybe I can even, because I was following along, maybe I can even just show you. Did I get this showing up? No, I didn't. I think I must have changed it, unfortunately. Oh no, I did. Okay, so here very quickly, you can see when I saved this image, when I was just following along yesterday, it produced this warning inside the Jupyter notebook. So that's just a piece of output that's being output to standard error. So standard error and standard out are just two ways of receiving output from a program when it's running. If it's normal, it just goes to standard out. Anything, any warnings of errors go to standard error. And both of those get taken by Slurm and written into your slurm.out file. So here we got two warnings from plot 9, and so it's put those into our Slurm output file. So those were warnings only. Warnings say, you know, there's something you ought to be aware of. Something isn't maybe quite as it should be. So I think here it's complaining about the size of the image, I believe. But whatever the concern is, it's nothing that's enough to actually stop it from running. So it goes ahead and does it. It's just there for you to be aware. So that ran, and we've now got scatterplot.png. And, you know, I have every reason to believe that that's correct. So I would copy that back to my computer and take a look at it. If it were a TIFF file or a JPEG, I could also log on to ARCHER2 with X11 forwarding enabled, as I showed earlier, do my module load, ImageMagick. Oops, missing a load. That would just tell me it doesn't know what ImageMagick is. We do module load ImageMagick, and then I would do display scatterplot.png. That won't work here because I don't have X11 forwarding enabled. So I need to log out and log back in with that -X option added to my SSH command. Okay, so I hope that's enough for the two groups of people. The people who wanted to look at GG at plot 9, and who wanted to look at using for loops to automate data output. Any questions just now? Thanks. You're very welcome. You're very welcome. Yeah, it seems strange. I'm not sure why it's warning. Does it warn even if it's a very small image? Let's see. Oh, okay. Thanks, Stack Overflow. Let's see what they have to say.
Yeah, just checking Google. It seems that by default prints these messages. I think there is a way to disable them, but yeah, it seems that are like more informative rather than a warning.
Yeah, it just seems odd, you know. Whenever you see a warning, you sort of get a little bit, you know, oh, should I be worried about something? But maybe it's completely unnecessary there. Okay, that's great. Thanks. Thanks, Edubia. You're very welcome. I hope you had a good time. I hope it's useful for you. I hope you have a good weekend. I'm very much looking forward to the next couple of days hopefully be a bit relaxing. So I hope all of you can have a break too. Be nice. I'm just going to, for the sake of it, log in to ARCHER2, just so I can take a look at that plot I just made. So I've just logged in here with a -X to enable X11 forwarding. Oh, I'm a bit small. Let me make that big. I'll just do module load image magic. And then CD to my work directory. What did I call it? Exercises. Plot 9 exercise. There we go. And if I just do display scatter plot, of course it won't work because it's a, yes, doesn't like PNGs. In which case I'll forget about that and I'll redo it with a, I don't know, let's just change it to a JPEG. Send that job off to run. And hopefully in a second it will complete. So at least it's running. At least I didn't break the code just by changing ping to JPEG. And it's completing. Okay, there we go. And if I display scatterplot.jpg, I should now get my image. Oh, and it is huge. It's taken over the entirety of my other monitor. So maybe this is why it's complaining, I'm not sure, but it is very big. I can make that smaller if I maybe change those options on the code. Let's, I don't know, let's make this what, 3 by 3 maybe, 3 by 2. Let's make it unbreakable, I hope. Okay, so we've only got one participant left now. I think everyone's feeling the call of the weekend, but I'm still happy to wait here until 5 o'clock, just in case there are any more questions or anything. Okay, let's try displaying the new version of scatterplot.jpg. Excellent, so am I. I'm also at home. Makes things much, much, much better. Ooh, I haven't typed the file name properly. There we go. That's, well, it's better. There's certainly some formatting needed. But this is, well, this is the point of the exercise, seeing of the challenge, seeing how we can change the things like the text size and everything.
The only issue that I see, for instance, there is that like the points are, if for instance in the previous one, okay, was way bigger. I think was the DPI maybe. because it was bigger, but you see
possibly.
that now the points are like a quite condensed.
Yeah. Let me change that again. So you reckon change it back to 10 by 10? Oops. 10 by
Yeah,
10
maybe 10
and
by 10 and maybe DPI maybe 150 or something.
yeah,
Yeah,
sure.
I don't know. Yeah, is what you said. It's like a question of playing and check
Mhm.
what is the best.
I seem to recall that journals I've published in have insisted on images being a certain DPI and then them being, you know, a horrific size. But given we're just playing around here, let's just see. I think I might drop it even further, maybe just 100. Let's see how this looks.
Yeah, you're right. I know. Yeah, some journals tells you like the DPI to, and that's also a good feature of Python that you can set DPI. Get.
Yeah, I remember one of them I was using insisted on everything being in encapsulated PostScript, which was tricky. Let's see how that's doing. There we go. I think that's okay. That's all good. Looks good. That's a new image. Let's try display scatter plot. Oops. And of course, haven't even changed the alpha or anything on it, which also helps to make it look better. Oh, there we go. That's a little better.
Yeah.
Much better. I can see the ggplot2 stylings of it. I've only ever dabbled in R myself, but I remember thinking the default style of the plots it made were quite recognizable. The sort of grey gridded background there. Graphics is always a terrifying word, but you're very welcome. Yeah, you're very welcome. Hope it was useful for you. Yeah. So yeah, have a good weekend.